So today we'll be doing slightly more advanced multi-level models where we'll be looking at repeated measures data in the first bit and then multi-level logistic regression models in the second bit. So for those of you who were here in last week's class, if you remember, we ended with a multi-level random slopes model. So the very first bit, which is the longitudinal repeated measures data, it's exactly the same multi-level model as a random slopes model. So it should be quite familiar to you if you understood what a multi-level random slopes model was. Okay, so before I go into the lecture slides, just a reminder about the different files that you would have received. So you should all have received the a zip folder called Multi-Level Workshops 1 and 2 Materials. So please download it to your computer and extract it. So make sure you don't double click on the zip folder, but extract it so that your computer can see all of the files. So once you've extracted all of the files, you'll see a whole bunch of files listed here. A lot of them are the TXT files. The text files are data files, and the .r files are R-script files. So, and they're all taken from the Lemma website. So again, for those of you who weren't here last week, the Lemma website is a specialist online learning multi-level. Yeah, this is the Lemma website based at the University of Bristol, and so all of today's materials are taken from that. Yeah, so it's free to register, and it goes into very great depth about different types of multi-level models, and yeah, so all of today's practicals, well, nearly all. Some of it are stuff that I made myself, but for the latter half of today's workshop, we'll be looking at module 6 and 7, multi-level logistic regression models. So that explains why you have so many files in the zip folder. They're all coming from this Lemma website. In addition, you have a few more files. I'll just go through them. So 7 refers to module 7 on the Lemma website. So module 7 is multi-level logistic regression models. Bang, I think, is one of the data sets that we are using for logistic regression. It's from Bangladesh, so BANG to start with. C refers to concepts. So if you want to learn more about regression analysis, multi-level analysis, logistic regression analysis, do refer to these concept chapters, again, taken from the Lemma website. R refers to the R practicals. So I've taken little snippets of the R practicals for today's workshop. But if you want to delve more into the R practicals, especially understanding why is it that you're using a particular command, then these give you a lot of in-depth knowledge. And last week, I also mentioned PO. So I often use PO to, because I can't remember a lot of the commands myself. So PO on ChatGPT will tell you, will give you some answers, mostly correct, about trying to explain different R commands for fitting multi-level models. The additional files, so function relates to the first bit of today's workshop, which is the repeated measures analysis. So the data sets that we'll be using for the first bit are function. The R script file is function. So we're using these particular data sets for the first bit. So let's make a start on today's workshop. So first of all, let's have a revision of multi-level concepts and multi-level linear regression analysis. So if you remember, whenever you fit a regression line, y equals alpha, the intercept, plus some slope parameter, the beta, times x, plus some residual error term. So this is the slope parameter. It's the unit change in x. Sorry, the unit change, how much y changes for a unit change in x. And this is the intercept over here. And these are the residuals from the individual data points. So that's a very simple linear regression line. And when we've got a no explanatory terms in the model, this is what the line looks like. So you can imagine there's a y-axis over here, and you've got a line with no relationship to any x variable. It's just a line that's parallel to the x-axis, and all it does is give you the intercept, which is the mean value of y, as well as the residuals. How much unexplained variance there is in the model. So the very basic multi-level model is a very simple decomposition of this overall residual of this overall variance into two components. The first component is the variance at the group level, the difference between the group mean and the overall mean. So the difference between the group mean and overall mean. So these are the group level variances. Usually we denote them by U. And then the individual level residuals around the group mean. So that's the E1H at the top over there. This is another individual level residual to the group mean. So this is just a very simple decomposition of the overall residual into two parts here. The group level variance and the individual level variance around the group mean. So that's another illustration of the decomposition of the total variance into these two components. So beta naught is just the overall mean of y, and beta naught plus uj. So uj is the group level variance, is the mean of y for a particular group j. So the uj is the difference between the group j's mean and the overall mean. And the eij is no longer the total variance, the total residual, but it's the difference between the individual data point and the residual between the individual data point and that particular group mean. Then we've got the variance partition coefficient. So remember, we've got two kinds of variances: the group level variance and the individual level variance around the group mean. So we can calculate what proportion of the total variance is attributable at the group level. So that gives us the variance partition coefficient. It's like the correlation, except it doesn't go less than 0. So it goes between 0 and 1. So usually we use it as a rule of thumb or as a rubric to say, okay, if there's 20% of the variance is attributable at the group level, then yes, it looks like it's useful to use a multi-level model. If it's less than 1% of the total variance is attributable at the group level, then maybe you don't need a multi-level model. So that was a multi-level model, but with no explanatory terms. Now we can add in explanatory terms. So here we've got age as a predictor of weight. And what's different is that we have, instead of a single intercept, we have multiple intercepts being estimated over here. So a different group mean for people living in York compared to Leeds, compared to London, compared to Hull. So what we're getting over here is a variation in the intercepts. So we're modeling not just a single intercept like we had over before, but we're modeling the variance in the intercepts, saying, okay, that living in these different cities, so being part of a group, has an effect on the average levels of the y variable, on the average levels of weight. So this is the most common type of multi-level model. So and in fact, most multi-level models just stop here because they're saying, okay, we're taking into account the fact that there are differences between the groups in the overall y value, and once we take that into account, most multi-level models say, okay, that's all we're trying to do is sort of trying to take into account the fact that there are differences in our dependent variable by the group levels. And it does this by modeling the variance in the intercepts. So we get the variance estimate in the intercept. So the residual terms do not differ at all. So they're just the group level residual and the individual level residual. So they don't differ, but what does differ is now we're getting the meaning of beta naught, the intercept changes. Yeah, so it's just beta naught plus uj gives us the intercept for group J, and that is it's not a very complicated model, as you can see. It's just two error terms, and then you can fit in as many explanatory variables as you need, in as many x variables. So the last type of model that we discussed last week was the random slopes model. And here you'll see that the slopes are no longer parallel because we're not fitting just a single slope, but a different slope for each group. So the effect of the x variable on the y variable is different for each group. So not only are we fitting a random intercept, but we're also fitting a random slope. So we're saying that there's an overall slope, and we're also fitting a departure from the overall slope. So that is what is underlying these terms. So we now have a much more complicated variance part. The intercept residuals for the group and the slope residuals for the group. So the overall group residuals has been split into two parts. The intercept residual for the group and the group level residuals. So the group level departures from the slope, plus of course the individual level residuals around the group mean. So and this comes at a lot of costs to model assumptions because we're assuming that these all these variance terms follow a bivariate normal distribution with constant variances, and as well as there is a covariance, there's a correlation between the U0Js and U1Js, the intercept and the slope variances that we estimate. So, okay, so that was all of last week's class. And this week, we're doing growth curve models. So repeated measures models that are exactly the same thing as the growth curve models. The only specificity is that the x variable in a growth curve model is always a time variable. It can be age, it can be years, it can be occasions. It's always a measure of time. But your y variable can be whatever that you want to explain. So the interesting thing here is that the individual is no longer at the level 1. The individual is at level 2, and the occasion, the time that you measure, or the time that you observe and measure, the weight or whatever you're interested in y, is at level 1. So the observation, the period of observation becomes the lowest level, and the individual becomes the level 2. So that's the other interesting thing about growth curve models, is that we're having the time unit as level 1. But in terms of specifying the multi-level model, it's exactly the same as a growth curve model. And last week I was trying to tell you why should we fit such a complicated model? Because most of the times, actually, I was at a seminar a few weeks ago, and the sociologist was giving the seminar, and he said, in sociology, nobody needs to fit random slopes models. You don't need that kind of complexity. Most of the times we just need to fit a random intercepts model. We don't need to model all this complicated variance at level 2. And I kind of think that's not necessarily true, but the one area where you definitely need a random slope is when you're estimating growth curves. Yeah. So for those of you with kids, you know that when your kids are growing up, you refer to growth charts as to whether or not your child is growing at an expected way for their age. So they grow these kinds of random slopes multi-level models to get at what is the acceptable amount of variability in their height or weight growth for their age. So we can't just have a single slope, a single line, because of course children vary between each other. So what the growth curve model does, it gives us what that expected amount of variability is. It estimates the variance in the growth rates for different children, and that is only made possible by these kinds of random slopes models. So they're very, very important for height and weight growth. Maybe less important for social sciences, but even there, I would agree they're quite important as well. So the kinds of examples for these kinds of growth curve models is where we're looking at differences in the growth rate, especially between, say, boys and girls, or changes in our health, such as our blood pressure as we become older. So we need a growth curve model for that. So what does the data look like? So we have repeated observations. So for this person, subject 1, we observe their Y value, maybe their health at time 1, time 2. We don't observe it at time 3, but we observe it at time 4. And for this person, subject 2, we observe their health at all 4 time periods. And for this person, we observe their health at time 1, time 3, time 4, but not at times 2. So the fact that there are missing data is not an issue, is not a problem for growth curve models at all. So it's a very nice way of sort of estimating the variance in our dependent variable, even when we don't have the data collected at a particular time point, or even if the data are collected at different time lengths. Yeah, say the difference between time 1 and time 2 is 1 year, and time 2 and time 3 is 2 years. That also is not a problem for a growth curve model. So it's a very flexible model. But what we do need to do is to transform our data from the wide format to a long format. So as you can see here, this first person who's in group A has the age of 45. At time 1, maybe they were 11 years old, 12 years old, 13 years old, times 1, 2, and 3. So we need to transform it so that each line is no longer a single person, but each line is a single observation time point. So because each line, remember, each in a repeated measures growth curve model, the level 1 is the occasion. So each line cannot be an individual. Each line has to be a time occasion. So we now have the first line. It's person ID 1 in group A, and their, say their age was 45. And yeah, so their X value was 11 at time period 1. In time period 2, their X value was 12, and in time period 3, the X value was 13. So you can see that this one person has been split up into three rows, and similarly, the second person has been distributed into three different rows. So now our unit of analysis, remember, each row is a unit of analysis, is no longer the person, but the occasion that we measure the person. And these occasions that we measure the persons, 1, 2, 3, are grouped within a single person. So the person becomes level 2, and the occasion becomes level 1. It's, conceptually, it's just like when you had a person, different people belonging to one group, and another set of people belonging to another group. So conceptually, it's the same as a standard multi-level model, but one in which the period is at level 1 and the individual ID is at level 2. Statistically, it's exactly the same as a random slopes model. We have two kinds of residuals at the group level. We have the intercept variance at the group level and the slope variance at the group level. Yeah. So the overall, this gives us different intercepts for each group, and this gives us the difference in the slope parameter for each group. So the X variable is now T, denoting time, but you can call it T, you can call it X, whatever. But the key here for the fixed part for this part of the equation is the beta 1Js. Yeah, so this beta 1J is telling you, so before, for the random intercepts model, it was just beta or beta 1 times Xij. But now we've got a J subscript for beta 1, which is telling us that this beta 1 is not fixed. It varies according to U1J. Yeah, so this beta 1J is actually beta 1, which is the overall slope, for everybody, plus the group level departures from that overall slope. And in addition, so we get these two variances, the intercept variance at the group level and the slope level variance at the group level, plus the covariance between the intercept and the slope variance. So that covariance is very important. We need to estimate it because this gives us an idea as to whether the lines are becoming wider as X increases or T increases, or if they're becoming smaller as X or T increases. So if you remember last week, for positive correlations between the intercept and slope variances at the group level, the lines are fanning out. Yeah, so they're becoming more wider as X increases. But for negative correlations between the intercept and slope residuals at the group level, the lines are fanning in as X increases. So we can observe that. We'll observe that in some of the practicals that we do. So this is some slides about the interpretation. But we've gone through it all so far, and yeah, this gives you the interpretation about the lines fanning out or lines fanning in. Just one thing to note for those technically minded is that the variance. Remember, we've got two kinds of variances at the group level: the intercept variance and the group level variance. And the group level variance is a function of our x variable. It changes as x increases or decreases. So when you add up these two variances, you get a quadratic function. Quadratic function of time, you can see here, time or our x variable is a squared term. So that means that it's not a linear function of the variance. It means that we've got either a variance slope that's either decreasing in a curvilinear level way or increasing in a curvilinear way. So as I briefly mentioned before, one of the advantages of a multi-level model is that you don't need to have equally spaced data, so that each time period doesn't have to be exactly 1 year apart. You can be, different years apart, and you can have missing data, under certain assumptions that the data are missing at random. So it's really, it's a really flexible model to model things like differences in growth rates, and then you can think of adding at different geography levels. So you've got occasion times within a person, within say neighborhoods, for example. So you can think of a 3-level growth curve model. And then you can have different x variables, different time variables. It doesn't have to be a linear function of time. It can be polynomial. We can put in a squared or cubic function of time. And you can add more covariates to those, to your explanatory variables. Sometimes growth models are known as latent trajectory models. So those of you coming from psychology might be more familiar with latent methods of modeling growth curves. So, and they're almost the same, but not entirely. So there are 1 or 2 technical differences between using a multi-level approach to model growth curves versus a latent variable approach to modeling growth curves. Now, I won't go into that, but substantively, they mean the same thing. So even though the models might look quite different, substantively, they mean exactly the same thing. So the other way of modeling growth curve models is not to run it as a multi-level model, not to run it as a multi-level model like this, where you've got occasions clustered within individuals, but to run it like a wide model using the wide data set like this. So you can run a growth curve model using a latent variable approach using this wide data set. It will give you substantively the same results, but technically there are 1 or 2 small differences. But I'm not going to go into that here. So the data set that we're going to use is a longitudinal data set that comes from a study in the UK that I was part of. It's a study of civil servants in the UK and the study of their health, their physical functioning. So I think the measure is called physical health functioning, and a high score is good. It goes from 1 to 100, and a low score is bad. So anybody 50 is the average. So anything more than 50 is great. Anything less than 50 is not good. So these civil servants we collected data from them repeatedly on 6 measurement occasions, approximately 2 to 3 years in between. I was interested in whether their civil service grade, if they were in a high grade status job or low status job, whether that affected their chances of health as well as their slopes of physical functioning, and how this varied from person to person. So the types of questions we would ask is, does physical functioning decrease as people get older? So, you can guess probably yes. But how does this vary from person to person? Yeah. And especially, does the decrease in physical functioning, does it become faster if you're in a low status job compared to a high status job? So these are the kinds of questions that we'll be answering in the in the practicals that we'll be doing right now. And this gives you an idea of the data set. Now, it's 2:30 now, so what I'll do is I'll go through some of the commands in R, and then I'll let you go through the rest by yourself, and then we'll take a break, and then we'll come on to the logistic regression part. Okay, so the data set, you can, the R script file associated with the data set is called function. You can just double click on function, and it should load up the R script from within RStudio. And then right at the top, you see I put in a whole bunch of install packages and libraries to run. So if you remember last week I got stuck because one of the commands wasn't working. We got an error, and that's because I hadn't installed the right package before before using another package. So it's and you know, Paul wasn't telling us why we were getting the error message. So the sequencing of installing these packages is really important in R. So you know, we can if you install all these packages, it'll take a little bit of time actually. So it took on my laptop about, you know, a few minutes, up to 5 minutes to install all these packages. So you can install all of them now and let it run in the background. So install the packages and install the libraries. So up to line 30. So you can run it now. I've already done that over here just to get a little bit of time. So while let R run in the background while I'm talking through. And then on line 39, we've got the read the data in. So it's this function.csv. So if we double click on that and run, it will bring up the data object my data wide. So it's the wide data of the civil service data set. And if you click on the data set, you'll see what the data set looks like. So it looks like we've got person number 1 who belongs in the occupational grade number 2, so the middle grade, and these are their physical functioning scores at different time points. So these physical functioning scores, they have a bit, one of the things that you'll notice straight away is that they have negative values here, -20. So that's probably missing data. So we've got to do something with the missing data before we start analyzing. Okay, so now we've got to then transform this into a reshape the data from the wide to the long data set. So we can use the R command reshape to transform the data from wide to long. So this reshape command specifies what data set you want to reshape. It tells R which are the variables, the different variables you want to reshape. So it's PCS1 to PCS6. We want to reshape into the long format. And then we want to create a new time variable, occasion variable called wave. And we're using the ID variable as the ID variable. And then we want to call the long health variable, we want to call it PCS. Yeah, so these are the explanations behind what this command does. So when you run it, we'll have created a new long data set called MyDataLong. And if you click on that, you can see instead of having 6 different PCS scores, we just have 1 column for PCS scores, the physical health functioning scores. But you also see that it's not clustered within a person. So the first line is person 1 who belongs in group 2 and their wave 1 PCS scores. but the next line should be person one again, again belong to group grade 2, but in wave 2. So the data needs to be sorted in this way. So that's what this this next command does. It sort of sorts your data so that it's in the right way, so that we order our data so that you use the ID variable. You sort the data by ID and then by wave. Yes, by the individual ID and then by wave. So if you click that, it generates a new data set called sort data, the sorted longitudinal data set. And you click on that new data set, you'll see that it's been sorted in the right way. So the first 6 rows now relate entirely to person number 1, and they're clustered within these different waves, 1 to 6, and their physical health functioning scores. So it's very important that you do this before running the multi-level analysis, otherwise you'll get completely nonsensical results from the multi-level analysis. Yeah, so your data, remember your individual, your level 1 units, your time units always have to be clustered within level 2, within the individual. Yeah, so your data have to be sorted correctly. Then the other thing that I mentioned that was problematic was that some of the values were -20. So describe the data set, tells you the summary of the variables in the data set, and you'll see that for the summary data of PCS, the physical health functioning score, we've got some values of -20. And we can visualize that a little bit more if we do a histogram. So I won't explain how to generate a histogram, but it's quite easy in R. I mean, you have to type in a lot of code. So, but of course, you never remember all of this code. So we'll just copy and paste the code from somewhere. But the important thing is to tell R what the data set is, what the X variable is, what histogram we want to generate, and the fact that you want to generate this histogram. So we're using this ggplot command here. And this shows you quite clearly that the -20 values is not an outlier. It's really something to do with missing data. So we need to get rid of it first before running the analysis. So that's what this command does. It says make the values of PCS of -20 into not applicable, so treat them as missing data. So if we run that, and now if we do the histogram, we get, those -20 values are no longer there. So we've got the data set in the long format, and we've got we've dealt with the missing data. It might seem really basic that I'm telling you to look at your data, but it's very important, because nearly all the mistakes I see in running complicated statistical models, they happen with people not doing their descriptors properly. So check the distributions of your X and Y variables, and also we need to check the distributions of our Y variables within each of the clustering, the group levels. So we can do that visually. So this is just a visual scatter plot of the physical functioning scores for each group. Yeah, for each person. You can see for person 1, we've got 1, 2, 3, 4, 5 data points, and in general, their physical functioning starts off at the average and then it declines over time. For this person, their physical functioning is relatively stable over time, and then for other people, there's maybe a bit of a steeper decline. Although this person only has 2 data points, for that. You can see this person, number 14, has just one data point. So it's really useful to run these kinds of descriptive analysis. In fact, it's important that we run these kinds of descriptive analysis before you actually run the model. So that's what this next set of commands does. So it's saying, generate for the first 20 individuals a scatter plot of where we've got time as our x variable and physical functioning as our y variable. So that's what these commands do. So that's what the ggplot does. So our x variable is wave, which is the time variable. Our y variable is PCS, which is the health variable. And it's telling R to first generate the scatter plot, which gives us the dots, as well as the smooth regression line, which is this fitted regression line around those scatter plots. And the rest are sort of ways to make the graph look slightly prettier. So yeah, so all of this is doing really important things, descriptive analysis before running the regression model. And now, once you're satisfied that you can fit a regression model, the data are looking okay, they make sense, then the command to fit a linear regression model is LMER, so exactly the same command as last week. We can often you don't need to write in formula equals, but for completion, we can say formula equals the dependent variable PCS is a function. There's no explanatory variable, so it's just an intercept over here, the constant term, plus we've got an explanatory variable here, which is a time, and we've got a quadratic function of time and time squared, so wave and wave squared. So a polynomial function of wave and plus 2, plus, and this is the variance part. So here is what makes it a random slopes model. We've got a random slope being estimated at the wave level. So wave is also a random slope. So the other thing that you notice here is we've put in wave underscore c. So we've centered wave at the mean wave. And this is really important when you're running growth curve models, is that your time variables should nearly always be mean centered, because it has better statistical properties. So mean centering your x variables, your time variables, is really critical in a growth curve model. And what happens is that we get a model. Let's see. Okay, so I will perhaps let you loose on to let you do all of these exercises by yourself. But what you see over here is one of the predicted charts from the models. So we've got the physical functioning decreasing on average as people become older, as wave increases, but also variability in that decline between people. And that variability, you can see, is increasing as wave increases. So for some people, they have a much sharper decline in physical functioning as they age. And for other people, they have almost no decline in physical functioning as they age. So because we've got a lines fanning out pattern, there's a positive correlation between the intercept and slope residuals. So if you have a high intercept, that means high intercept residual, that means you will have a high slope residual. So that gives us this lines fanning out pattern that we observe over here. And then we can also try to explain this variability between people. Why is it that some people are declining faster in terms of their physical functioning than other people? Is it because maybe these groups of people are the low status people and these groups of people are the high status people? Yeah. So we can explore the interactions between a level one variable, which is the time, and a level two characteristic, which is the characteristic of the individual, the status of the person. So that's called a cross-level interaction, and see whether maybe that explains some of that variability, that increasing variability in physical functioning as people get older. And yes, it does look like for people in the lowest grades, grade 3, they have a much steeper decline in physical functioning compared to people in the highest grades, that's in grade 1. So this cross-level interaction, it's a cross-level interaction because time is at level 1 and grade is at level 2. So this cross-level interaction is sort of explaining some of this variability in the growth rates, in the negative growth rates, as people get older. So I'm going to let you loose on R now. So I think you've all opened up this R script file. So what I suggest you to do is just to go through the commands in there, and it'll take you. Of course, you can just run all of the commands. Maybe try to understand them a little bit as you're running it, and then we'll start again with the next. We'll take a little break, and then we'll start again with the next part of the workshop. Okay. So just to give you an indication of time, it is now 2:50. So I suggest you run all of these commands. We take a break at about 3. So between 3 and 3:10, we start again. At 3:10 past 3, we start the multi-level logistic regression. So now I can't look at it sorting on the code here, but you can have a long data set included with the dots. Okay. Called function underscore. Yeah. The transform data set is here already. It's
So
just,
this one is the long.
yeah, that's the long format. Then you just need to read it and it's just some
Yeah,
problem with
sure,
the-
sure, yeah, I'll turn this one, thank you.
So condition is x1, x2, x3 all relate to the same variable. They're all their health or so it's the same variable measured 3 times. But repeated measure. Only if it's repeated measure, then you combine it into the long one. It's the same variable measured 3 times. We don't analyze it in the white format, we analyze it. This is called the panel. Panel we create a single panel variable. So X variable is now whatever variable is measured repeatedly. ID. This one is the person. ID. Person ID.
There's 4 different patients. That's our second one. Okay, so which is for this station? This is 2. It's more easier to
to the multi-level model is.
Yeah. So this is for us, this is for two.
Yes.
For us. I got it. Illustrate it with it has arrow here.
So let's talk after the class or have a little presentation. Okay, so let's come back to the class again. And for the final bit of today, we'll be discussing multi-level logistic regression models. But before doing that, let's have a little refresher of logistic regression models and why we use logistic regression models. So far we've been using linear regression models. So we're assuming that our dependent variable has a continuous distribution. It has usually, a normal distribution, but it doesn't have to be a normal distribution. The key thing is that the residuals from our linear regression model, we assume to have a normal distribution. But what if our dependent variable is not height, is not weight, but it's more, it's a category. So like what we find in social sciences, most of the times we have categories like social class or ethnicity or, different kinds of preferences, whether people have strong opinions about something or less strong opinions about other things. So the kinds of data that we have are usually categorical, and the most basic kind of categorical data is a binary data that are either 0 and 1s. Yeah, so yes and no's, 0 and 1s. So we can't use a standard linear regression model approach. Why is that? Because of several reasons. Yeah, because what happens is if our data are bounded by 0 and 1 from a linear regression model, we would get predicted values of our dependent variable outside of 0 and 1. So it doesn't make sense. But statistically, there are a whole host of other reasons besides nonsensical predicted values. Things like, as we approach the boundaries of 0 and 1, you can see that the amount of variance changes. Yeah, the ability to, you can see in the middle at the mean, there's a lot of ability to have a lot of variance, but at the zeros and ones, the amount of variance is bounded by these boundaries. So the variance changes as x increases, as x goes from 0 to 1. So really, there's sort of nonlinear effects going on as you go from 0 to 1, and we've got this problem of unequal variance. So treating it like treating our dependent variable, our binary dependent variable, as though it's a continuous variable is problematic because of all of this nonsensical predictions, but also this statistical problem with the variance. Thankfully, there's a very simple way of solving the problem, which is instead of analyzing our binary variable as it is, as a 0 and 1, we take the logit transformation. And this is the logit transformation. It looks a little bit complicated, but I'll explain it a little bit. So this is the linear model, y equals beta naught plus beta 1x. Yep, you're all familiar with that. The logit transformation is instead of analyzing this, we analyze the logit, which is 1 over 1 plus the exponent of beta naught plus beta 1x. So I'll explain what the logit is. And what this logit transformation does is that it bounds our predicted values between 0 and 1, and what it becomes meaningful. So we get we also get this thing about the logit transformation is this S curve over here is denoted. So that's the logit function, and you can see it's not a linear curve; it's a curvilinear curve, and so it solves this problem of nonlinearity as we approach the boundaries of 0 and 1. So that's another reason for using the logit function, and I mean there are a whole host of other sort of statistical reasons for why we use the logit function, why we model proportions. One of them is that when we have small denominators, so say we've got only a few sample cases over here, that can result in high estimates of the variance. So the variance really depends on the denominator. So it's really good to model, instead of modeling the 0 and 1, we model the proportion or the logits. Yes, so this is an example of the logit function, which gives us this sigmoid curve. Now, what is a logit? A logit is the natural log of p, which is probability, divided by 1 minus p. Yeah. So people understand probability. Probability and proportions are the same. So p denotes the probability of having a 1, and 1 minus t is probability of not having a 1. Yeah. So the probability of, say, if binary variable is alive or dead, and dead is the 1 and alive is 0, so p would be the probability of being dead versus the probability of not being dead, or probability of being alive. So if we take the logit of that, so the logit is you take the natural log of p divided by 1 minus p. P divided by 1 minus p is the odds. So those of you who are betting people, you might be more familiar with odds. Odds are, as you can see, are kind of like proportions, but not exactly. Yeah, the odds is p divided by 1 minus p. Yep. So the proportion is just p. Yeah. So the odds and proportions are they go together, but the interpretation of odds is that you only need two numbers. Yeah. the number of people who have the characteristic of 1 and the number of people who don't have the characteristic of 1. Yep. So let me see if okay, I've got a few more examples later on. So it's very easy to calculate the odds once we know the proportion. And once we know the odds, we can take the log of that. So the log of the odds is the logit. And that is what we model in a logistic regression model. We model the logit. Instead of modeling the binary variable, we model the log of the odds. So, you know, a lot of people, they don't like logistic regression models because they don't understand what is an odds, what is an odds ratio, how does it relate to proportion. And this is just a simple way of telling you, well, we all understand what a proportion is. Yeah, once you know what a proportion is, you know what an odds is. Yeah? Once you know what an odds is, you know what a logit is. Yeah? So we're modeling the logit instead of modeling the binary variable 0, 0, and 1. So it has very nice statistical properties. But before coming on to that, here's a quick reminder of the relationship between odds and proportions and logits. Yeah, say you've got, you know, the proportion is 50%, 5 out of 10, you know, and the odds is 5 to 5. Yeah, 5 out of 10 is the same as 5 to 5 odds, or 6 out of 10, 60% is odds of 6 to 4. Yeah. 6 divided by 10 minus 6. And 8 out of 10 is 8 to 2. It's 8 divided by 10 minus 2. Yeah. So 8 to 2. So the proportion of 0.5 is the same as having the odds of 1. Yeah? So you won't make any money if you bet on a horse with the odds of 1. Yeah. You might make a little bit of money if you bet on a horse and with an odds of 1.5, yeah, so long as the horse wins the race, and you make a lot of money if the odds is 4. If you have an odds of 4, so how do you get 1.5? It's just 6 divided by 4. How do you get 4? It's just 8 to 2. So betting on a horse that wins and with an odds of 8 to 2 is great, you know. But of course, the reason why the odds are so high is probably something to do with the horse. So once you know the odds, you can take the natural log of that. The natural log of 1 is 0. The natural log of 1.5 is 0.41. The natural log of 4 is 1.39. Yeah. So, you know, once you know the proportion, you know the odds, you know the logits. And vice versa, once you know the odds, you know the proportion as well as the logits. And once you know the logits, you can work your way back to the proportions as well. So this is just a long-winded way of saying, you know, don't be put off by, you know, modeling the log of the odds, modeling the logit. What does it mean? It is related to the proportion. But statistically, it's not the proportion. It's proportion divided by 1 minus the proportion and taking the log of that. So the logistic model, which is just the logit, is the left-hand side of the model looks unfamiliar, but the right-hand side of the model looks very familiar. Yeah, beta naught, the intercept plus the slope parameter for x1. But the left-hand side of the model, so instead of having a y variable, we've transformed our y variable, our binary variable, into a logit. Yeah, so our y variable, which is binary, is a proportion. You know, how many zeros are there, how many ones are there. We take we calculate the odds and we take the natural log of that. That's all a logistic model is. So we're, you know, it's help you become familiar with that, and it solves all of the statistical problems that I noted before. You know, it gives us bounded predicted probabilities. It solves the problem with the variance because our variance is really dependent on the sample size as well. So the one thing that you might have noticed that is different. So what's kind of missing here? What's missing in this equation compared to, say, a linear regression model? No residuals, yes, no error terms. In a logistic regression model, you don't have any error terms because of our error, our variance is a function of the proportion, proportion and the sample size. So in any logistic regression model, you never get any residual terms because we assume that our logistic regression model follows a binomial distribution. Okay, we're not doing probability, so we won't go into binomial distribution, but that is the assumption that we make that we don't need to estimate what the residual is because we know what the residual is because it follows a binomial distribution, and the binomial distribution is we know what that looks like. So no error terms is needed to be estimated for a logistic regression. Of course, that works for a single-level logistic regression. If it's a multi-level logistic regression, we will estimate a residual term at level 2, but not at level 1. Yeah. No error term at level 1 for a logistic regression model. So let's talk a little bit about the data set you'll be working with. It comes from a data set of Bangladeshi women of childbearing age. And it's about finding out what predicts a mother of childbearing age in Bangladesh receiving antenatal care. So for those of you who come in the health sector, this is very important that the expectant mothers get access to a doctor or nurse or a trained midwife because it reduces their chance of having complications in their birth and improves the chance of both the mother and child surviving. So it's a data set that just wants to explain, we use it to try to explain what increases the chances of a mother receiving antenatal medical care. Is it something to do with whether the child is the firstborn, secondborn? So this child to be born, is it the firstborn, secondborn, thirdborn? You can see this data set was collected quite a bit of time ago. So birth order ranges from 1 to 13. So there's some mothers who've had 13 children in the data set. The mother's age, of course, could be really important, whether they live in an urban or rural area, the educational level, whether they have no education, primary education, or secondary education or higher, the mother's religion, and how wealthy the household was. So immediately you can see that some of these factors could be really important for understanding whether or not the mother received antenatal care, whether she had access to, maybe they had money to pay for this doctor. And also you can see that some variables are at level 2. So urban is a typical level 2 variable because it denotes the neighborhoods or the places where the mother comes from. These are just direct screenshots from the practical 6.5R, but it just gives us a cross tabulation of anti-medical care by mother's education. So mother's education 1, 2, 3, primary, no education, primary education, secondary education. Yeah? And 0, 1, so 0, no antenatal medical care. 1 is they received antenatal medical care. So this just gives you the cross tabulation, how many mothers there are in each of these two categories. These categories for these two variables. Of course, it's very hard to see the overall pattern. You need to calculate the proportions. So we can calculate, for example, the column percentages. So 68% of mothers who had no education had no antenatal care. And 32% of mothers with no education had received some antenatal medical care. You contrast that with the educated mothers. So 3 is secondary school or higher. So 73% of mothers who had secondary school education received antenatal medical care, in contrast to just 31%, 32% of mothers who had no education. So these are just our commands to get at the proportions, and also the proportions of 0 and 1s. 49% without any antenatal medical care, if you add all of these rows up, versus 51% who had antenatal medical care. So about 50% of the mothers did and didn't get antenatal medical care, but you can see it really depends on the level of education of the mother. So we know the numbers. So let's start calculating the odds. So this is a little bit of a refresher on odds. So the odds of receiving antenatal care for a mother with no education, so we're looking at the ones. Mother with no education equals the ratio of the number with anti-med 1, so 594, to the number with anti-med equals 0, 1272. So to calculate the odds, we just divide 594 by 1272. So we can ask R for that. Is it 594 divided by 1272? Yep. So the odds is 0.46467. Yep. And similarly for the other ones, we can calculate, we can also calculate the odds of receiving antenatal medical care for a mother with primary education. So this 2 column over here. So it's 793 divided by 856. The odds of receiving antenatal care for a mother with secondary level education is 1366 divided by 485. Yeah. So it's very easy to calculate that. And once you calculate the odds, it's easy to calculate the odds ratio. So the ratio of the odds of primary to no education is 1.984. So the interpretation is that the odds of a primary educated mother having antenatal medical care is almost double the odds of a mother with no education. And similarly, the odds of a mother with secondary or higher level education having antenatal medical care is almost 3 times the odds of a mother with no education. So this gives you some idea about how you translate probabilities into odds ratios. Yeah? So the odds ratio is the usual metric that we use to compare groups from a logistic regression model. So how do we run this in R? So remember, this is a very simple single level regression model. We use the GLM command, the generalized linear model command. Our dependent variable is anti-med. We have 2 independent variables, 2 dummy variables for education, mother's education 2, mother's education 3. The data comes from my data, and the family equals binomial logit tells R that you want to run a logistic regression model. You can run other kinds of binary models like probit models. Probit models are very popular. You get the same, you get the same interpretation, but the coefficients will change. Because with the probit models, you get probits instead of logits, but the interpretation is exactly the same. So for those of you who are more used to them coming from health sciences, from the medical sciences, logistic regression models are very, very popular. For those of you who are more economists, probit models are very, very popular. So it really depends on the discipline. There are reasons why medical science people prefer logistic regression models. They like odds ratios. They're more familiar with odds ratios than probits. But I'm digressing there. So it's just a disciplinary thing why we use logistic regression models instead of probit models, but they're all the same thing. So we can fit this model and we can see what these the odds are. So this gives us the log odds. Yeah. So remember this model, we're fitting the logits, the log of the odds. So that means the coefficients that we get are not probabilities, they're not odds, they're the log of the odds. Yeah. So the logit for mothers with primary level education is 0.685. And if you just compare that, well, maybe it's slightly different from the numbers here, but it's it would be this number over here, but it's not exactly the same. So it's not exactly the same data I'm looking at, but and the logit, so the log of the odds for a mother with secondary level education is 1.796. Yeah. And we can see that these coefficients of the logits are highly significant, so they're definitely different from 0. So once we get these log odds, what we can do is it's hard to understand what logits are. I mean, nobody understands what logits are. I mean, it's really hard to understand. But we have a more intuitive understanding of odds and odds ratios. So to calculate the odds ratio, we can just take the exponent of the logit. So taking the exponent of the logit gives us 1.98, and taking the exponent of this logit gives us 6. And to do that in R, we can just tell R we want the exponent of a particular number. Now, the thing with some people, they don't like odds. They say, I really find it hard to understand what is an odds ratio. So it's easy to sort of translate. Once you know the odds, you can translate it back to probabilities. Now, you don't have to hand translate it yourself. You can use R. So you can use this particular library in R. So you say, tell R you want to get the predicted probabilities from your fit model, and it will translate those logits, yep, these logits over here into probabilities. Yeah, so 32% of mothers with no education have antenatal medical care, and 74% of mothers with secondary or higher level education have antenatal medical care. So yeah, the significance tests, you can look at the t-test, the z value, it's highly significant, lots of very small p-values, and then we can construct confidence intervals around the logits. So remember, we get these logits. To construct a confidence interval, it's just a logit plus or minus about 2 times the standard error. So that gives you the 95% confidence intervals between 2.5% to 97.5%. But remember, these are confidence intervals around the logits, not around the odds ratios. So to get the confidence intervals around the odds ratios, you need to take the exponent of those fitted coefficients. Yeah, so take the exponent, and this gives us the confidence intervals around, say, 1.98. So the lower confidence interval is 1.72. The upper confidence interval is 2.27. And for mothers with secondary level education, the lower confidence interval is 5.23. And the higher, the upper level confidence interval is 6.95. So this also illustrates something about logistic regression model, is that the 95% confidence intervals for the odds ratios are not symmetric. Yeah, So they're not equally spaced. They are equally spaced. They're symmetric around the logits. They're symmetric around the logits, but not for the odds ratios because we're dealing with the exponents. So we're taking the exponents of that. So that's another thing people get confused. It's like, oh, the tails and the whiskers for the odds ratios for the 95% confidence intervals are really, they're not symmetric, but they're not supposed to be symmetric. Then we can test different hypotheses. We can test whether, the hypothesis that both education dummy variables are significant. So again, so just as a reminder, so this is the t-test over here that gives us the z value. So whether individual coefficients are 0. Yeah. But what if we want to test whether both of these coefficients are 0? For that, we can't use the t-test. We use a wall test, and we can do that in R using this particular library car. So we just type in the command linear hypothesis, and it will give us a hypothesis test for whether both of these education variables are jointly 0. So on 2 degrees of freedom, we're using up 2 variables. The p-value is very, very small. So in this particular case, not only are the individual coefficients for education very unlikely to be 0, but it's very unlikely that both those coefficients are likely to be 0. Okay, so that was just a refresher for logistic regression models. For the multi-level logistic regression models, it's very much the same thing. There's no added complexity. I mean, the one added complexity is the U0Js. Yeah? So we are estimating a variance at level 2 in our logits, but everything else is the same. Yeah? So we're still estimating the log odds. Beta naught is the same, beta 1, beta 2, beta 3, all of these slope terms are the same. The only difference is that we are now estimating a random part of the model. But the interpretation of the slope and the coefficients are exactly the same as in a logistic regression model, and the interpretation of the U0Js, the random part of the model, is exactly the same as in a linear regression model. So, okay, we don't need to go read that text. And, just like we got the predicted probabilities from a single level logistic regression model, we can get the predicted probabilities from a multi-level logistic regression model. But it's a little bit more complicated, but we go through the exercise in R that tells you how to do that. So the response variable is exactly like in a linear regression model. In the data set that you use is exactly the same data set. We now have, it's also the same variables. We also use a few extra variables that we derive from this data set. So we'll start with the R script file 7.1.R. So let me just load that up. Yeah. So if you want to follow as I'm going along, 7.1.R, we can read in the data file, call it my data. And the important thing is to install the packages LME4. So LME4 is the package for doing multi-level models. And so we use the library. So you can read in the data, and I already installed the packages. So it'll give you a prompt saying, do you want to? Sometimes it gives you a prompt saying, do you want to reinstall, reload R? Just say yes. Okay, so we've read in the data file, and it's called My Data. So this is what the data file looks like. Yep. So it's each line is an individual mother. So you've got some identifiers over there, the community ID and the woman's ID. So each line refers to a different woman. So the woman's ID changes for every row, but the community ID, so that's all of these women in this top part of the data file belong to one community. And as you scroll down, you'll see the community ID changing. So once again, it's important to note here that all the women are sorted within each community. So this data set is sorted in the way that R needs to be for it to be analyzed in a multi-level way. So remember, each individual ID has to be sorted within the higher level ID. So your data set should look exactly like this. So that's another common mistake. Lots of people say models don't run because the data are not sorted in this fashion. So our dependent variable is the receipt of antenatal medical care. That's 0 and 1. So and then we've got the explanatory terms over here. So let us fit a two-level model. Yeah. So to fit a two-level model, we've got to first run the library of LME4, and the two-level model. The new command is glmer. Yeah? So remember, to fit a linear regression model, it was just LMER. But to fit a logistic regression model, a multi-level logistic regression model, we have to add in the G. Yeah, so generalized linear model, G for generalized. And we've got to tell R that we want to fit a logistic regression model. So the binomial in brackets, quotations logit tells it you want to fit a logistic regression model using my data. And this is a model with no explanatory terms in there. You can see it just has a constant, and we want to estimate a variance at the community level. So it's not very interesting model, but it just gives us these fits. So the intercept, so it gives us an intercept over here, as well as where are the random terms? So it gives us the random effects. So this gives us the group level variance. It gives us a group level variance, and it's okay. This is kind of interesting. So it's giving us a standard deviation of 1.21 and a group level variance of 1.464. Now the mistake some people do is they say, okay, we use a t-test. We just divide the coefficient by the standard deviation, and that would be entirely wrong. Yeah, so we can't use these standard deviations to see whether or not the variance is at the community level is significant, because this standard deviation test doesn't really apply to variances. So yeah, we'll see. We'll use another way of estimating whether or not we need a multi-level model. But before doing that, we just need to be aware that fitting a multi-level logistic regression model is quite complicated. In fact, it's very complicated and takes up quite a lot of processing power on the part of your computer. So it uses algorithms to find the solution, and with binary data, it's quite it can take a long time to arrive at a solution. So in nearly all statistical software, they use shortcuts, so approximations of these algorithms to arrive at a solution. And these approximations kind of work, but they're not really great for estimates of the variance. So for the fixed parameters, Over here, we just have the intercept. It's fine, but for the variance terms, there's, these, like over here, the variance at the community level is 1.464. And because of the shortcuts that the algorithm uses in R, it might be that this variance is not well estimated. There's bias in it. So the proper way of doing variance estimation in multi-level logistic regression models is to use Monte Carlo Markov chain estimation methods, which we definitely won't go into today. So that's a whole another lecture, but it's a Bayesian process. And in fact, I've given in the folder you've got an example of MCMC estimation. But for that, you really need to have a good understanding, some understanding of Bayesian modeling. So it's just a little check to say you can run multi-level logistic regression analyses and using R, using these what's it called? It's called Laplacian estimation methods. But the reviewers who know their stuff will, if you're trying to publish it, they'll say, oh, what's the algorithm that you used? And then if you say you use Laplacian, they say, okay, but you need to check to see whether your variance estimate changes if you use another estimation method. So, but most of the times for very simple models, it really doesn't. But it really does matter when you're estimating very complex multi-level models with lots of variances, different variances being estimated. Okay, but for these kinds of simple models, this approximation will work fine. So we can display the results of the, using the summary command, and yeah, I think we've gone through this already. Yes, so we test to see whether a two-level model is needed. So remember I was going on about how we shouldn't use the t-test here. So this is the random effects. So that's the variance 1.464. That's the standard deviation 1.21. So we can't divide this by this. We can't use a t-test. So how do we know whether we need a multi-level model? How do we know whether the variance at the community level is significant? Does it significantly improve the fit of the model? So that's what the next few slides do. So first we can test the model fit with and without the two-level model. We can compare the model, the single-level logistic regression model to the multi-level logistic regression model. Can compare the model fit, and that's what this test does. Yeah. So we can. This is first we run the very simple logistic regression model where it's just the dependent variable. There's no explanatory variable, just the intercept, the data. It's a logistic regression model, so we call it fit A, and we compare the log likelihoods to the model fits of the two models. So we get a test statistic of 7998. So -2 times the 399.83. So this is the difference in twice of the log likelihoods is what we're looking for, and we're looking, and this is 1 degree of freedom because we're estimating the variance at the group level. So it's 1 degree of freedom. That's the only difference between fit A and the previous model fit. So we're saying that the improvement in the model fit is very big. How do we know it's very big? Because the change of 800 on 1 degree of freedom is very, very, very significant. Yep. So usually, I should know this, anything less than 3.8, I think it's 3.8, would be not significant at the 5% level. So anything larger than 3.8 on 1 degree of freedom is a very big improvement in the fit of the model. So we can test for whether or not we need a multi-level model using using this statistical test. And alternatively, we can calculate the community level residuals to get at the scatter plots. So if you remember the community level, the caterpillar plots of the community level residuals. So if you remember in a linear regression model, this is the distribution of the residuals ranked from the lowest residual to the highest residual. And this is the line of no effect. So this is saying that there are a lot of communities that have below average residuals. They have lower than average levels of antenatal medical care. And these are communities that have higher than average levels of antenatal medical care. So this is saying, yes, you probably do need a multi-level model, because look at this big difference in the community level residuals. Yeah. If all of the community level residuals were around zero, and these confidence intervals were all overlapping with zero, then you probably don't need a multi-level model. So those are the two ways of testing to see whether you need a multi-level model. So you look at the caterpillar plot, or you can test for the change in the deviance from one model to the next. It's exactly the same as in a linear regression model, so nothing new there. And then that was a very boring model because we don't have any explanatory terms in there, but of course we can add in explanatory variables like mother's age, mother's education, and so on, and see what happens to the variance, especially the variance at the community level, the U0Js. So that's what the next few exercises get you to do. It also gets you to calculate the predicted probability. So as I said, it's relatively easy once you know how to do it in R. And we need to first run this package, this library VGN, to get back the predicted probabilities, and then to get at the predicted logits. So it's explained much better in that, but it's, once we've got the predicted probabilities, this is mother's age over here. And if you remember, it was a random intercept model, so there was no slope term estimated for variance in the slope term for age. So as mother's age increases, the predicted logit, the predicted log odds of getting antenatal medical care declines. So that's saying older mothers have lower likelihood of having antenatal medical care compared to younger mothers. Maybe older mothers feel that they don't need it, or maybe older mothers have less access to antenatal medical care compared to younger mothers. We can add in a quadratic term for age. So instead of just a linear term for age, add in age and age squared. And the model actually finds that the age squared term is not significant at the 5% level, but we can just keep it in. If you look at the predicted probabilities, it doesn't really change that much. So it's pretty much still, it's not like there's a big curve being introduced when we introduce the age squared term. So the rest of the exercises get you to add more model complexity by adding in more explanatory variables and adding in random slopes for those explanatory variables. So let me just talk a little bit about that, and then let you loose on the data set practicals for about half an hour, and then we can finish then. Okay. So there are two ways of adding model complexity. We're sort of adding more explanatory variables like mother's education, and then that's a simple random intercepts model. And then we can allow for mother's education, the slope, to vary between communities. So to estimate a random slope or random coefficient for mother's education. So first of all, remember what I said about random slopes, which is it's important to mean center your variable if you're running a random slope or growth curve model. So first of all, we create a centered value for wealth that is, you just subtract the mean from the value of wealth. So it's just mean centered. And we use that in the model. So instead of wealth, we use wealth C, wealth centered. We include mother's age, the age squared, mother's education, and the mean centered value of wealth. And you'll see as you go through the exercise that when you add in these variables, education and wealth, it reduces the between community variance. So the level 2 variance. So the level 2 variance is here. It was about 1.2 before in the models without any explanatory terms, and it's reduced to yes, it's reduced to 0.929 in these models with the explanatory terms. So it looks like taking into account the socioeconomic characteristics of the mother explains some of the between community variance in antenatal medical care. So maybe, it's like some communities will have higher proportions of educated women and wealthier households who have greater access to antenatal medical care. Now, to calculate the variance partition coefficient, it's a little bit different from a linear regression model because we don't have a level 1 variance. In logistic regression, there's no level 1 variance. So one way of getting around it is just fixing the level 1 variance to be 3.29. So there's a reason why it's 3.29. It comes from the binomial distribution. But basically, the variance partition coefficient is just the variance level 2 divided by the variance level 2 plus 3.29. So it's a quick way of calculating the VPC, but then it comes with certain assumptions, which we won't go into here. But yeah, it's a very easy calculation of the variance partition coefficient. And then we can also estimate a random slope for wealth. So in this model, it's starting to get more complicated now because we've got the coefficient, so the slope effect for wealth has a J subscript. So if you notice here, there are no J subscripts for any other explanatory variable except for wealth, because we're not estimating a random slope or random coefficient for any of the others except for wealth. So here we're thinking that the effect of wealth differs between communities, and to fit that, we just need to include 1 plus wealth. Yes, so we need to include wealth in the in the random part of the model. So wealth is not just in the fixed part of the model; it's also in the random part of the model. And this will give us a whole bunch of random effects. So the group level intercept, the residuals, the variance at the group level, the slope variance for wealth, the variance in the effect of wealth, but of course no individual level variance, because it's a logistic regression model. So what this then does, if we look at the predicted, the other thing that I didn't highlight in the output was the covariance. Yes, So the correlation between the group level intercept variance and the group level slope variance is -1. So it's very highly correlated and it's negative. So you get a lines fanning in pattern. So if we look at the predicted probabilities of antenatal care or predicted logits of antenatal medical care by wealth, yes, that's the wealth index, it goes from 1 to 5. The negative correlation between the intercept and slope residuals means that you get a fanning in pattern rather than a fanning out pattern. Fanning out pattern would be the correlation or covariance between the intercept and slope residuals is positive. So what this is saying is that, of course, mothers who are more wealthy have more access to antenatal medical care. Yeah, the predicted logit is higher. The predicted logit of antenatal medical care is higher if you're 5 compared to the 1. But there's a lot of variation in the communities for low educated, for poor mothers. There's much more variation in antenatal medical care for poor mothers compared to wealthy mothers. For wealthy mothers, nearly all of them have access to antenatal medical care. But for mothers who are poor, you can see there's a lot of variation in receipt of antenatal medical care. So that's one of the reasons why we would run a random slopes model, because it's looking like the effect of wealth differs by characteristics of the community. Yeah, and it's probably something to do with how wealthy that community is. So in the final examples, it asks you to create a community level characteristic of wealth and use that as an explanatory term. So let me see. Oh, but before doing that, we used wealth as a continuous explanatory variable, but we could also have used wealth as a categorical explanatory variable. Yeah, wealth has 5 categories, 1 to 5. So in this model, we, instead of treating wealth as continuous, we treat wealth as a categorical variable, and we also have a random coefficient for the most wealthy mothers. So the interpretation for this random coefficient is exactly the same as the random slopes model, where we had a random slope for a continuous wealth variable. So it's virtually the same way of fitting that in R. So the one thing that we haven't done is to add in contextual level variables. So here, that's kind of the whole point of running multi-level models, because we want to see what is the effect of living in a particular area, in a neighborhood, in a city, on your outcome variable. So here we add in urban, so whether the mothers live in urban, rural situations, and to see how that changes the community level variance that we estimate. So I realize this is a lot to go through, it probably is better if you go through it by yourself, than me trying to explain what each one of these practical exercises is trying to do. So can I suggest that you start with 7.1, the R script for 7.1, and you work your way through 7.1, 7.2, there's no 7.3, 7.4, 7.5, and 7.6. And each of these exercises is just an elaboration of the model, like the way I've told you. Yeah, so it's first of all adding more explanatory terms, it's adding a random slope to those explanatory terms, and then it's adding saying, okay, what if we added in some contextual level variables. And then the final one is it's looking at a cross-level interaction. So it's getting you to do something like this. So we've got the household wealth index over here, and the predicted probabilities of antenatal medical care. And these bars represent how wealthy those communities are. The blue ones are very poor communities, and the green ones are very rich communities. So we can get what the predicted probabilities of antenatal medical care for mothers of different wealth living in wealthier or poorer communities. So what we can see here is that if you're a mother in of low wealth, of the lowest wealth category, then your chances, there are very big socioeconomic inequalities between communities in access to antenatal medical care. But if you're a rich mother, then it really doesn't matter which community you live in, whether it's rich or poor, you will still have very high access to antenatal medical care. So you can see over here that, yeah, this data really does suggest that you need a random, a complicated multi-level model, a random slopes or random coefficients model to really tease apart the differences between the receipt of antenatal medical care for different mothers in different communities. Yeah, so that's what that final 7.6 R script file will do. And it's a little bit of a challenge because, I started today's workshop by saying, the sociologist who was at the seminar said, yeah, we don't need complicated random slopes models. You can understand perfectly fine with random intercepts models. Actually, for some cases, and this is a social science sociology type question. Yeah, we kind of do need random slopes models. So, okay, so I've talked nonstop for quite some time now. So why don't you, for the next half an hour, go through 7.1 to 7.6, and I'll be here to answer your questions. Oh, before you do that, can you please give me your feedback? If you could take this QR code and give me your feedback. Thank you for giving me your feedback last week, also for this week as well.